Hi guys, BuildZoid here, and today we're going to be taking a look at this thing. So this is a Gigabyte Z97X-SOC. This is a motherboard from back in the day when Gigabyte still made extreme overclocking motherboards, except they're going to start doing that again. Well, really extreme overclocking focused motherboards. It's not like their more recent releases haven't been capable, it's just like they didn't come with this many they don't come with this many buttons until there's a Z590 board that I'm pretty sure everybody already knows what I'm referring to. But yeah, boards like this finally have a successor. Boards like this one. But anyway, this board's kind of interesting for multiple reasons. One, this is an engineering sample board. It's not a retail version, which is why the heat sinks look like this. What's interesting about this board, well, so it's an engineering sample. Got rescued from an electronics recycler, which, as far as I know, they really shouldn't be well, it's not really a rescue since they were selling the boards, but yeah, which they really shouldn't be doing because it's an engineering sample board and you shouldn't really be able to buy these. But I'm not going to complain about that because I get to have a really cool motherboard thanks to the fact that somebody was able to get one, like buy one of these and then send it over to me. So yeah, big thank you to the person who got this board to me. They also sent along a few boards that I find significantly more interesting because they're just kind of better. See, the thing behind the idea behind this board right here is that Gigabyte wanted to create a budget extreme overclocking motherboard. And so you've got all the extreme overclocking buttons, right? You've got your power button, your reset button, your clear CMOS, your core ratio up, down, BCLK up, down, slow mode, voltage read points, postcode, dip switch for enabling and disabling PCIe slots, dip switch for enabling and disabling DIMM slots, which is pretty cool. This is also cool. It's just pretty common. Like there's a lot of motherboards with that. There's not a lot of motherboards with this. And the main idea is like if you were running your memory on liquid nitrogen, well, you probably don't want to be pulling memory sticks with an LN2 pod attached to them, so you can just turn them on and off with that. That's pretty neat. Or if you're just messing I mean, you could also just be lazy and not want to pull a memory stick out even if it's on like air cooling. Like who cares? Like you can use the switch whenever, but especially if you have an LN2 pot mounted to your memory sticks and you've got 4 sticks and 2 of them are causing issues, or you just want to test something with 2 sticks instead of 4 sticks, well, you've got a switch for that now. So that's really cool. So yeah, you've got all these extreme overclocking features over here. You've got USB ports that, you can, like, for test bench use. There's a clear battery button, which I'm not really sure what that's supposed to achieve, because that seems like a second version, like a second clear CMOS, which, yeah, I don't get that. There's dual BIOS on the motherboard, and of course you have the switches for actually controlling the dual BIOS functionality, so you can choose which BIOS chip you're on, and you can also disable the automatic dual BIOS functionality that the board comes with. And so you have all of these extreme overclocking features. You've got PCIe lanes laid out for, 4-way crossfire, 2-way SLI, because the crossfire will run in 8444, I think. It might be 4444, I'm not sure. Whereas SLI, you need to run 88. There's no PLX chip in SLI. Quad SLI requires at least 32 PCIe lanes, though technically you could, well, 4-way SLI requires 32 PCIe lanes. Quad SLI only requires 2 X8 slots because you can use GTX 690s and 590s and Titan Zs. Oh, there was also the dual GTX 760. So boards like, so GPUs like that with their own built-in PLX chips, so you could run quad SLI with those. Anyway, so we've got all these extreme overclocking features. Oh, of course, auxiliary power for the PCIe slot so that you don't melt your 24-pin when you're running 3 or 4 GPUs. Of course, in the most convenient location ever, right in the middle of the board. Like, it makes sense because, like, the 12-volt power plane for the PCIe slots runs basically like this, as far as I know. It basically looks something like that. So this is a totally reasonable place to put that power connector based on where the power plane goes. But if you think about it from the perspective of, like, where am I going to run the cable, that kind of sucks. Anyway, but you do get the extra PCIe power there. Now, the other thing that I wanted to talk about with this board is the VRM, because that's where the cost cutting kicks in, right? Like, so far, it's like all very good. We've got all the overclocking buttons, all of the overclocking stuff, and then you get to the VRM, and it's like 1, 2, 3, 4 inductors. And then, of course, under the heatsink, we only have 4 power stages. And they're not even really high current ones. And so you look at this, and it's like, if this was on a $200 Z370 motherboard, I would consider it completely unacceptable. If this was on a $200 Z68 motherboard, I would also consider this completely unacceptable. If this was on a Z39, if this was on a $200 Ryzen motherboard, no, please no, just no. But the thing is, on a motherboard like this, it's still not ideal, but it's nowhere near as bad as it would be on, say, a Sandy Bridge board or a Ryzen board or a Skylake. Well, Skylake, actually, you could probably get away with this. But a Coffee Lake, you couldn't, because Coffee Lake pulls about 50% more power than a Skylake does. On a Haswell board, this is actually mostly okay. And the reason why it's mostly okay is because of the Haswell fully integrated voltage regulator, which means that if you want, because the thing is, like, let's say you're maxing out a 4790K on ambient, okay? So you're probably going to top out somewhere, in terms of power draw, you're going to top out around 200 watts running, AVX workloads. And that would be at like 1.3 volts core voltage, which we're going to round down to 1.2 because some idiot didn't put 1.3 in my notes. And at this point, I don't really feel like fixing that. So we're just going to go with 1.2 volts, which is unrealistic, but, yeah. Actually, I think 1.3 volts, you still wouldn't be hitting 200 watts. I think you need like 1.4 to hit 200. It's been a really, really long time since I've worked with a 4790K. I should get some measurements on that. Though, unfortunately, I do have a 4770K, don't I? Or does it? No, I think I have a 4670K and no 4770K. We can still, like, the thing is, you can technically take the non-hyper-threaded CPU and add 30% to that, and it's probably pretty close to what a hyper-threaded CPU pulls in terms of power. Just fun fact, hyper-threading gives you about 30% more performance and about 30% more power consumption. Funny how that works. But anyway, yeah, so you wouldn't really even be reaching like 200 watts, so 200 watts of power, let's say, which you're not going to hit, so where was I going with this? Idiot. 4-phase VRM, IR3564B voltage controller, 4-phase controller. Power stages are IR3553s, so those are 40 amp power stages. And the thing is, you can get away with this because let's say you were running a Haswell at 200 watts. Well, you would be running, say, 2 volts output voltage on the VRM, 100 amps into the CPU, right? 2 volts, 100 amps, that's 200 watts of power. But it's only 100 amps, so the VRM would only be producing about 19 watts of heat, which this block of aluminum that really is more of a thermal capacitor than it is an actual heatsink would actually probably do an okay-ish job of dissipating. And I say okay-ish job of dissipating because I would actually expect this to hit about 100 degrees after running for about an hour. Yeah, I think if you ran this for about an hour, also depends on your airflow. If you have a lot of airflow, you could probably keep this at 70 degrees just fine. But yeah, that's the thing is, like, 19 watts of heat at 200 watts output power, that's really not bad. Whereas if you were trying to run 200 watts without the magic that is the fully integrated voltage regulator that the Haswell CPUs have, let's say you were pushing 1.2 volts and you were trying to do 200 watts of power draw. Well, at 1.2 volts, 160 amps would produce 36 watts of heat. So about 17 watts of heat more than 2 volts at 100 amps. Because the main loss of power the main source of power loss in a VRM once you get into the high current draws is not like the switching losses of the MOSFETs, which are basically fixed. Like, you need to turn the MOSFET on, you need to turn the MOSFET off. That costs some amount of energy. And then you, of course, have the losses from just the switching process itself. Those are relatively fixed. Those don't really change depending on, like, with how much current you're running. But then you have the actual, like, losses due to the resistance of the MOSFETs. And, well, that's I squared R. So if you double the current, your heat output ends up getting quadrupled. And so by reducing the output current but raising the output voltage, you can get much better power, like much more efficient power delivery out of really terrible power delivery. Right? You can get away with a 4-phase like this. It'll still run hot. Okay, like don't get me wrong, it'll still run pretty hot, but if you tried to do 200 watts on this at 1.2 volts, it would just kind of overheat. Like it wouldn't be, oh, it runs hot. It would be, oh, it overheats and shuts down. That's assuming it has thermal protections, which it really should, because this is an IR3553. That's a power, that's a power stage with a bunch of built-in. I don't think it has built-in shutdown, but it should be able to tell the controller, hey, I'm overheating. And assuming the controller is properly configured, that should turn the VRM off. So that's kind of the thing, is like, yeah, Haswell's fully integrated voltage regulator means that you could get away with a VRM like this with a heatsink like this. It's got like 2 fins. Yeah, now that's what I call a heatsink. This isn't, now admittedly, this isn't the retail VRM heatsink for this board, but the retail version isn't really that different. So yeah, that's kind of the neat thing about Haswell. And honestly, we can blame Haswell for the fashion accessory VRM heatsinks that you would find on like Z170, Z270, Z370, Z390 boards, as well as just kind of the VRMs actually got quite a bit better, because Intel does publish a guideline of like, hey, your VRM needs to be able to output this much current. They just, that guideline, however, doesn't say, hey, your heatsink has to also be, your VRM thermal design has to be capable of outputting that much current for more than a couple seconds, which is kind of the flaw. Like the Intel's design guidelines are like, well, if you're using the stock turbo limits, right, like that's you only have to output X hundred, like over 100 amps for like a couple seconds, for like a minute. Which is very different from like full load with, a static all-core overclock, or just disable the turbo boost limit, right? Like you can also do that, and you'll still get the VRM to overheat. So Haswell's basically responsible for terrible VRM heatsink designs, and because on Haswell it just didn't matter. Haswell didn't pull enough power. And also the power that it did pull, it pulled at such high voltage that getting good enough VRM efficiency was super easy. Like Gigabyte wasn't the only manufacturer to have a VRM like this. In fact, there's a bunch of like Z97 boards, especially on the low end, which would have even worse VRMs than this, with no heatsink at all. And it was just like, yeah, it's fine. don't need to worry about it. It doesn't pull any it doesn't pull enough power, and the power it does pull is, easier to deliver than what you have to deal with on CPUs without fully integrated voltage regulators. So one of the biggest benefits of the fully integrated voltage regulator is like your motherboard's power delivery is way simpler, way more efficient, way easier to do. It's not overall, I'm not sure that overall the efficiency is much higher, because the fully integrated voltage regulator itself does have power losses, right? Like that's not 100% efficient. Every time you do a voltage every time you're converting from one voltage to another, there's going to be some power losses. But at least from the motherboard vendor's perspective, Haswell is really easy to deal with in terms of power delivery. And yeah, now the downsides to the fully integrated voltage regulator are things like, well, it doesn't work at really low temperatures. So Haswell has a cold bug, and depending on which version of the fully integrated voltage regulator you're looking at, the cold bug can actually be even worse. So Haswell, depending on the CPU, you're talking -130 to, actually, I think I've seen some chips do -140. But, so like nowhere near full pot is the main point. Right? So -130 to maybe a -100 if you have a really bad CPU. Then if you look at like Haswell E, you're talking like -120 to -100. Then we have Broadwell E, which is an absolute disaster. And like you can basically max out Broadwell E on dry ice, because the cold bug of the fully integrated voltage regulator for most Broadwells is around -90 degrees, which is like, yep, that's great. And then you get to, and then Intel, and what's really interesting is like Intel stopped using the fully integrated voltage regulator on their mainstream CPUs. And the thing is, as far as I know, one of the other benefits that it had was actually for laptops. Like the simplified power delivery on the motherboard, that's really useful if you're on like server hardware where you have 200, 300 watt CPUs these days. And that's why Intel keeps shipping fully integrated voltage regulators in their server chips. But they also had benefits for laptops, because in a laptop environment, you didn't have to charge and discharge the bulk capacitors every time you changed P states, right? Like if you go from a 0.8 volt P state to a 1.3 volt P state, you need to charge those capacitors by half a volt. And that's energy that you're just putting in those capacitors. That's not energy doing work in the CPU. That's just like energy you're putting into those capacitors. And then when the CPU goes from that high voltage P states to the low voltage P state, well, we need to discharge those capacitors, and you're just sort of throwing that energy right out the window doing that. So the fully integrated voltage regulator also had like benefits for laptops in that sense, where it was like, yeah, you could save some energy by not having to worry about charging and discharging the bulk capacitors. So I'm not really sure why Intel completely dropped the fully integrated voltage regulator from their mainstream CPUs. They still use it for their server chips because, well, you know, it's just better if your motherboard doesn't need to have 16 phases just to deliver 200 amps to a chip that runs at 1 volt. Right? Like, like the funny thing is a lot of server chips will actually run at less than 1 volt. So if you look at the TDP, so the actual current draw is higher than the power consumption, which is just atrocious for VRM efficiency. Because instead of talking like, oh yeah, we're going to be shoving, you know, like say 200, like a 200 watt chip pulling 200 watts, like 200 amps. No, it's like 200 watt chip pulling 240 amps. How's that? Because again, it's like, your power losses in the VRM from current are I squared R, so they get really bad really quickly. So yeah, Intel still uses the fully integrated voltage regulator on server chips, but it doesn't use it on mainstream parts, which, yeah. And they did on Haswell, and thanks to that, Haswell just destroyed VRM heatsink design for several generations of motherboards following it, because like until Z390, it was like your VRM heatsink was basically a fashion accessory rather than an actual heatsink. And the reason for that is, well, on Haswell, it worked just fine. It didn't matter. Like, who cares? You could probably get away with no heatsink on this if you gave it enough airflow. That would still be just fine. So, anyway, that's the main reason I wanted to talk about this specific motherboard. The Z97SOC is just like extreme overclocking motherboard with a freaking 4-phase using, and it's like they're not even using the good power stages. They could have used 60 amp power stages, but those are 40s. Okay, and it's honestly kind of okay. Now on LN2, I'm not sure how this works out, but I think like if you're not running long benchmarks, this will probably still be just fine. Because that's actually like long multi-core benchmarks, right? If you're running long single-core benchmarks, well, a single core, it doesn't pull anywhere near as much. It doesn't pull that much power. Oh, and I forgot to mention another benefit of the fully integrated voltage regulator is that it massively simplifies like your voltage, your power transients for the VRM here, much easier to handle because, well, they're at a lower current, like at lower current levels. But the other thing is the fully integrated voltage regulator runs at like over 100 megahertz switching frequency, so it is crazy fast compared to any motherboard level VRM, and it can get away with that because it's built directly into the CPU. You can't really do that on a motherboard VRM as far as I'm aware. So anyway, yeah, that's the power delivery on this thing. Thank you Haswell for ruining VRMs for several years. Let's take a look at the back. So this board is a 6-layer PCB, which was really surprising to me, because I really thought it would be a 4-layer, being that this motherboard was actually, like when I said low-cost extreme overclocking motherboard, it wasn't actually that cheap. Like it was still around $200 as far as I can tell. Yeah, I was honestly expecting a 4-layer PCB because it's like it's only got 4 phases. But no, this is a 6-layer PCB. So this is one of the few motherboards where you can say this has less power stages than it has PCB layers. Though I guess technically there's motherboards with no power stages, but if you ignore those, if you ignore those, this has less power stages than it has PCB layers, which is kind of funny. Because most motherboards with power stages will have more power stages than they have PCB layers. This is a 6-layer board. There's 4 power stages in the VCC in, and then there's 1 more power stage for the memory VRM over there, which is just like, yeah. So I find that kind of funny, though it doesn't really mean anything. But yeah, 6-layer PCB, T-topology memory layout. You'll notice there's no pins going through the motherboard, and that's because the board uses SMT DIMM slots, which help a little bit with signal integrity from, like they apparently help a little bit with signal integrity. Yeah, so that's that. And then we've got quite the output filtering for the memory power delivery over here. Interestingly enough, we have a bunch of unpopulated capacitor pads. So the person who sent this board to me actually like really wants me to cap mod this. So I guess we'll mess with that. I don't really expect to see any like benefit from doing that, but I do have a bunch of spare capacitors, so yeah, like there's nothing stopping me from messing around with that. But I really don't think it's going to do anything because DDR3 pulls more power than DDR4, but it doesn't pull that much more power. Um, yeah, is there anything else I wanted to cover about this board? Like the main thing for me with this board, because like Gigabyte has other boards with the SMT DIMM slots, and as far as like maximum DDR3 memory overclocking, Gigabyte actually has a two DIMM version of the SoC boards, and I actually have one of those two dimmer SoC boards now, thanks to the same person who gave me this thing. So yeah, we're gonna be taking a look at that eventually. I'm not sure when, but yeah. So you know, we've got pretty fancy memory topology on this board. Like basically, this motherboard is like all of the motherboard, none of the VRM. Which is just like, I find that absolutely, and this was extreme overclocking motherboard. What's also really funny is the 8-pin and the 4-pin, where it's like, this is going to blow up before you max out that 8-pin. And I'm completely serious about that. There is no way this VRM is capable of outputting the amount of power an 8-pin is rated for. Like, this won't do the power an 8-pin is rated for. And, well, maybe if you, like, if you use like chilled water cooling on the VRM, maybe. I guess you could dry ice cool the VRM, though I wouldn't recommend that because a lot of power delivery components don't necessarily function at super low temperatures. Oh yeah, like that VRM really is like that's a hell of a lot of power connectors for not like no VRM basically. So that's kind of fun about this board as well. What else is there? Not really much else, is it? Can't think of anything. There's nothing really special about the CPU socket, right? We just got some capacitors in there. Trying to think of anything that I'm missing. No. Not really. Yeah, interesting board. And thank you, Haswell, for destroying VRMs. So, well, more like destroying heat sinks. Like, the thing is, you still had, like, you know, Z97 and Z87 motherboards with really perfectly, like, well, much better power delivery than this. Actually, Z87 boards were quite excessive, some of them. And then the motherboard vendors realized, wait a minute, we don't need to bother at all for Haswell. And then they could just kind of, you know, kept not bothering until, like, Z390, which was not so great. So anyway, yeah, because like basically VRM power delivery, like heatsink design, and actual the VRMs themselves sort of crater around the Haswell motherboards. Like if you look at motherboards before Haswell, quite substantial VRMs with substantial heatsinks. If you look at motherboards like after Haswell, like Haswell is like the beginning. Well, no, even Skylake, like the Skylake boards weren't necessarily great, but they were better. Anyway, that's it for the video. Hopefully you found this somewhat interesting. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. And then there's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. Both the Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you check out the links to those in the description. So yeah, that's it for the video. Thank you for watching, and goodbye.